What's the acceleration of an object that speeds up from 8 meters per second to 12 meters per second over a distance of 80 meters? So let's start with the givens, as always, right? What information do they give us here?
The initial?
Yeah, they give us the initial, right? What's the initial velocity, Isabel?
8 meters per second.
Yeah.
Is it meters?
Yeah, meters per second, right? M over S is meters per second. So we'll give that our VXI, 8 meters per second.
And they give us the final velocity?
Yeah, exactly. Great. Which one's that?
12 meters per second.
Yeah. So 12 meters per second final velocity. And then what's that last given that we have?
The distance?
Mm-hmm.
Which would be 80 meters?
Distance is 80 meters. Good. And what symbol do I use for distance? Anybody remember? Distance or displacement?
Delta X.
Yeah, delta X. That's it. Great. Oops. So we've got VXI is 8 meters per second, VXF is 12 meters per second, delta X is 80 meters, and I switched off, but what was the unknown that they were asking us for there?
The acceleration. The
acceleration, right? They specifically said, what's the acceleration of that object? Good. So we've got VXI, VXF, delta X, and AX written down. So which big four equation is that going to be?
Wouldn't it be AX equals the final velocity minus the initial velocity over delta X? Like the first equation?
That's, yeah, it would, but the equation for acceleration that you're thinking of is this. So final velocity minus initial over time, not delta X, right? This is the equation.
That's what I was
so it's not going to be that one, but that's a good thought.
It's going to be the last one.
Yeah, it's going to be the last one, right? If we have VXF squared equals VXI squared plus 2 times acceleration times delta X, right? That's the last big four equation. That's got all our symbols in it. So we do need to rearrange this, right? We want to get acceleration by itself. So again, so this term in our equation, right? The 2 times AX times delta X, that's got our unknown in it. So we want to get this term of the equation by itself first. So to do that, we have to get rid of the VXI squared, which is added on. So what's the one step I need to do, or the first step I need to do to get the VXI away from the right side?
We need to subtract the initial velocity in both sides.
Great, yeah, we got to subtract the initial velocity, or really the initial velocity squared, right? So VXI squared minus VXI squared goes away on this side. I have to do it here as well. So I get final squared minus initial squared equals 2 times acceleration times displacement. And now there's probably just one more step I need to do, right? If I want acceleration by itself, but 2 and delta X are being multiplied onto it. What is one more step?
We need to divide 2 and delta X.
Yeah. Right, I want to get rid of the 2 and the delta X on this side. So if I divide by 2, it's going to cancel out. And if I divide by delta X, that's going to cancel out. And I'll do it over here as well. So to rewrite the equation I end up with, right, is the acceleration is going to be equal to final velocity squared minus initial velocity squared divided by 2 times delta X. Okay, everybody okay with how we rearrange that? So let's see what, sorry, go ahead.
No, my bad. All good.
Okay, no problem. Okay, so we plug in our numbers. We've got VXF squared, so that's 12 meters per second that we're gonna have to square, minus the VXI squared, so that's 8 meters per second that we're gonna have to square, and then divided by 2 times 80 meters. So let's see, I can do, so 12 squared, right? I don't have to remember to square them, minus 8 squared divided by, and I'll put in parentheses, 2 times 80. 143.6. So 143.6 meters per second squared, that's going to be our acceleration, which is a pretty high acceleration. But that's all right. Actually, wait a minute. Is that right? Yeah, I guess it is. Let me try it with parentheses. That doesn't seem right. But let me know if you get anything different than I'm getting. That sounds better.
Now. Yeah.
All right. What did you get, Jose?
0.5.
Yeah, 0.5. That's what I'm getting now as well. See, I made a mistake the first time, right, by not putting the parentheses around the 12 squared minus 8 squared. So it should be, see, I knew that seemed, I could tell I did something wrong, right? Because that's a really big number for acceleration. And it didn't look like slowing from 12 meters or going from 8 to 12 meters per second is going to be that big of an acceleration. So I recalculated, and again, a much more sensible answer. So 0.5 meters per second squared. Right. So every second that goes by, it just gets half a meter per second faster. Questions about the problem of the day for today?
I think it's all good.
Okay, great. Okay, so let's take a look at real quick tomorrow, or the problem of the day that's assigned today for April 1st. This one says, when traveling 75 meters, a bicyclist slows down from 13.2 meters per second to 4.0 meters per second. And we're looking for how much time that takes. Let's see, I don't know what's a good hint to give you here. This one seems pretty straightforward. Anybody not sure what any of those givens are going to be? I think
The problem is free fall, right?
oh, that's a good, is this one free fall? So this one's a bicyclist, right? So a bicyclist slowing down.
No.
No, you're right.
Yeah.
He's not falling through the air. He's just riding a bike and hitting the brakes, right? So this is one where that's a good thought. Yeah. So the acceleration isn't necessarily going to be 9.8, right? We can only use that when the object's falling. So that looks like the acceleration here is not a given and it's not an unknown.
Yeah.
Anybody else have any questions you see or comments from the problems of the day or anything? If not, thank you for joining today, and I'll see you again tomorrow. And yeah, I'll look forward to hearing you guys read tomorrow. Okay.
Bye, Miss.
All right, mister.
I miss
All right. Have a good day, everybody. Bye.